Welcome to Diagnostics. Let's explore an important topic shaping the future of defense and global security. I'm the founder and director of International Defense Security and Technology, a California-based nonprofit think tank dedicated to research and analysis on global defense, security, and emerging technologies. I also serve as CEO of Interplanix LLC, a New Mexico-based company advancing satellite risk analysis, orbital debris forecasting, and space security frameworks to ensure mission assurance and resilience. Previously, I served in leadership roles at India's Defense Research and Development Organization, DRDO. Most recently as Director of the Systems Analysis, Modeling, Safety, and Quality Cluster at DRDO Headquarters, New Delhi. This channel brings you deep insights into the global security ecosystem, from geopolitics and emerging military technologies to cyber, space, and system-level analysis of tech trends and their interrelationships. Subscribe and join us as we decode the forces shaping the future of global defense and human security.
Today we are diving into one of the most fascinating frontiers in science and technology: how tiny materials called nanomaterials are helping unlock the future of quantum computing, secure communications, and ultra-sensitive sensors. It all centers around something incredibly elusive: the single photon. At the heart of quantum technology lies the need to control and manipulate particles like photons, particles of light one at a time. And this is where nanomaterials come in. These ultra-small, precisely engineered structures have unique optical properties that allow them to generate single photons on demand, with exceptional purity and stability. That's a big deal. Now, why do we need single photons? In photonic quantum computing, for example, photons act as quantum bits or qubits. These qubits can exist in multiple states at once, unlike classical bits that are just zeros or ones. That means quantum computers could solve problems that are completely out of reach for today's machines. But none of this works without precise control of individual photons, and nanomaterials are making that control possible. Quantum dots are one key player here. These are nanoscale semiconductors that emit single photons when excited by a laser. Their size and composition can be fine-tuned to create photons at specific wavelengths perfect for encoding information or performing calculations. And in the world of quantum cryptography, that's crucial. In quantum key distribution, or QKD, if even one photon is intercepted, the intrusion is instantly detectable. No eavesdropping goes unnoticed. That's quantum security. Diamond NV centers are another star of the show. These are tiny defects in a diamond's crystal lattice that can emit single photons even at room temperature. They're incredibly bright and stable, which makes them perfect for real-world, secure communication systems. But it doesn't stop there. Quantum sensing is another area where single photon sources shine. These photons can help detect magnetic fields, temperature changes, or even tiny mechanical shifts with extreme precision. And materials like boron, nitride, nanotubes, and other two-dimensional structures are now being used to make sensors that are far more sensitive than anything we've had before. What's especially exciting is that researchers are now integrating light-emitting nanomaterials with silicon, bridging the gap between quantum optics and traditional electronics. Some have even developed carbon nanotubes that emit single photons in the telecom band at room temperature, perfect for future quantum networks. And it's not just carbon nanotubes. Silicon carbide, hexagonal boron nitride, and Perovskite quantum dots are all emerging as potential platforms for scalable, efficient quantum light sources. These materials don't just emit photons, they do it efficiently, with great control, and often without needing bulky or cryogenic systems. That's a huge win for scaling up real-world applications. Now, of course, challenges remain. Manufacturing these sources consistently and integrating them with existing photonic systems is no small feat. But researchers are making rapid progress. Labs around the world are now fabricating high-quality quantum dots, engineering defect with atomic precision, and even using nanowires to boost photon emission rates to millions of counts per second. It's an exciting time. Nanomaterials aren't just improving quantum technologies, they're enabling them. As we continue pushing forward, these tiny building blocks might just be the key to building entire quantum communication networks, ultra-secure cryptography systems, and sensors with unimaginable sensitivity. So, while the particles they deal with are microscopic, the impact of nanomaterials on the future of technology is anything but small.